Okay, so I think all we've established so far is that number 21 and 20.2 has way too many letters and confusing junk in it.
Confusing junk kind of
Okay, so I think I am supposed to calculate a line integral, right? Like that's fundamentally what they asked me to do. This dude here, line integral. So they want me to calculate a line integral around a curve where the curve is the circle of radius 2 centered at 1, 1, 1 in the plane x plus y plus z is 3. And they tell me it's oriented counterclockwise when viewed from the origin. Okay. So, to my thought, that means I need to go over 1, back 1, up 1, right? Dot. Right? Yes? And this plane, x, y, z, or x plus y plus z is 3. What is the normal vector to that plane? 1, 1, 1. Right? So pointing straight out that way. And so my plane, I think, looks more or less like this. That's a crap picture. Sorry, guys. So I have this dot, and my normal vector goes like that way. I'm having a hard time picturing this.
What is that word?
I'm having a hard time drawing this, rather.
Center.
You guys see that? And we're oriented. Oh, there's a circle in here too, right?
On the plane.
So there's a circle in the plane. That's like this. And it's oriented clockwise when viewed from the origin.
Yeah. Which is just counterclockwise.
Okay, which is oriented counterclockwise looking down at it, right? I'm not going to put that orientation on here because it'll cause you to maybe have your brain flip over if you're looking at this the other way. Okay, and then they tell me that the vector field F is given by all this junk. So, I'm not even reading that. So, how do I do this? What do I start with? Okay, so you have two options in life, right? You can parameterize this line integral the way it's been handed to you, right, and compute. Or else you could try
Stokes theorem.
You have a line integral, right?
Yep.
So you can turn a line integral into either a area integral using Green's or a surface integral using Stokes. Is Green's applicable in this situation? No, why not?
Three-dimensional.
Because it's in 3D, right? Correct. So I guess we're down to either parameterize this or use Stokes. I'm going to use Stokes because parameterizing this seems like a disaster.
Yeah, and if you look at it closely, Stokes basically clears out all the garbage when you try a cross product for the curl.
Yeah, and hopefully when I calculate the curl, things get easier, right? At the very least, I'll be able to slim this down to integrating on the graph of a surface, or the graph of a function, right? So like maybe I can make my life a little easier. You guys see that? So what do I need to check before I apply Stokes?
All those thingies, so let's see.
I need smoothness.
Yeah.
Do I have smoothness
Yep.
of the curve and the surface
Yeah.
and the function?
Yep.
Yes, yes, and yes. Is it oriented properly? I'll deal with that. Is it orientable?
Yeah.
Definitely.
Yeah, we could just flip it over if it's not.
What else do I need?
Simple and closed.
I need a closed and simple curve.
Yes and yes.
Yes and yes. Yeah, I need the continuous partials, which I believe there are.
Yeah.
I believe these partials are continuous everywhere, so I'm not really sweating that. You guys cool with this? Okay, so where is your surface?
Yeah, that's where we're having trouble.
I would make the surface that little disk,
Oh, right. Yeah, if that's what you
right?
Yeah.
So you have some curve, and then you have the inside of this thing. I'm assuming that's a disk. You could make lots of surfaces. Like you could make a half sphere. That would be an option. It will be messier, but you can do it. Like Stokes lets you pick. Right? All you need is a surface that has this curve C as the boundary. You can pick lots of stuff. I would pick the simplest thing possible.
Yep.
So, I'm going to Stokes this. When I Stokes this, what does it turn into?
An integral of S.
Double integral over a surface, right? Of what?
The curl of F d area.
Curl F dotted D area. You guys good with that? Okay, so first things first. Curl.
Yep.
Maybe I'll just go over here and compute things. Okay, curl of F is. Do I use that trick?
Oh yeah, let's just use.
Okay, so the trick is there's a Z, a Y, and an X, and then a Z, a Y,
and an X.
and an X, and then hang on, there's partials
Yep.
and subtractions.
Yep.
And then there's partials on the bottom.
So then I found this. Yes.
Yeah, thank you for finding this
Yeah.
stuff.
And then it's Y.
Okay, wait, hang on. So this is the which slot?
That's dy.
No, this thing right here is an X slot,
Can't put
right?
any X.
So there's not going to be X's in the partials, and they're not going to match. So Z's opposite, not X, is Y. Y's opposite, not X, is Z. This is the Y slot, so X's opposite, not Y, is Z. Z's opposite, not Y, is X. This is the Z slot. So that's Y's opposite that's not Z,
M's X.
X, and X's opposite that's not Z is Y. Also, this thing here, right, is what? Green.
Oh,
That is not a coincidence. Okay, now I put Z, Y's, and X's in here, right? What did I mean by those? Because the partial of Z with respect to Y is probably 0.
Yeah. You're talking about f of z, f of y.
Yeah, so this is like the Z component of my vector field F, the Z component, or the Y component of my vector field F, and so on.
Can I also just show one more shortcut? No.
Yeah, sure, what is it?
I just, we were doing that whole like, oh, z, it's not the x, and I'm just like, a really quick way is just cross,
Yeah,
cross.
that's how
Yeah.
I did it too.
Okay, cool. Nice. So, this is, what's the partial of the Z component with respect to Y?
Yeah, sort of.
It's partial of z. That's just 2.
2. That's not a partial, that's a 2.
I can see that.
Okay, what's the Z partial of the Y component?
0.
0. Okay, what's the Z partial of the X component?
0.
0. What's the X partial of the Z component?
-1.
And the X partial of the Y component? -1. And the Y partial of the X component?
2.
2. Oops, -2. So all told, I got the vector 2,
1, -3.
1, -3. Cool? Yes? Okay. So,
Now we need a dA.
I'm going to be integrating over S, that vector, 2, 1, -3, D area. You guys with me on that? Okay. And then you all were having a hell of a time parameterizing this thing, right? Yeah? Okay. You make your life
Yeah.
easier. How can you make your life easier?
You notice that the curl dotted the normal, the area vector is 0.
What? How?
Yeah.
Got a brain on him.
The normal vector is 1, 1, 1. 2 plus 1 minus
Oh.
3 is 0.
Okay, so for this thing, the area, right? You can think that guy there, right, is a unit normal times the area, right?
Yeah.
Which you could calculate. Or you could notice that this 2, 1, -3 dotted with some scalar version, right, of 1, 1, 1. Right, really I would have to scale that to normal, right? Oh, but that's 0 anyway, right? So it doesn't matter what your conversion factor is. This guy here is 0. Because the curl, right, of your vector field is always perpendicular to the normal vector on the surface. You guys see that? So what that is if you have your disk here, right? You're going around it some way. Where's your churn in your vector field that's going to help you get around this thing? Well, the churn, right, the curl, is always perpendicular to the normal vector. Remember those little paddle wheels? So the little paddle wheel is doing this thing, where it's going in there, out here. So there's a net flux of nothing. You guys see that? In other words, it's not going to help you go around this line integral at all.
Or is that no flux given cup?
Yeah, exactly. Where's my no flux cup? It's in my house. Okay. Cool? Questions, Steels? This trick of like, hey, if the surface you've got is flat, right, the normal's always the same, you can get a little bit something extra out of, oh, maybe I could just multiply with the normal and then multiply by the area. If this thing's constant, that's super easy, right? If one of these two things, either the thing you're integrating or the normal vector, if those vary, you're in rougher shape, right? Because you probably can't make this eyeball. But on this one, we're integrating a constant, and the normal vector is always the same. So we don't have to add these up. We can just multiply, see that it's 0, and then notice that if you add up a bunch of zeros, you get 0. Cool, cool? Good observation, Leslie.